Hi, I'm George MacKerron. I'm a TypeScript developer for Neon. Today I'm going to talk about the improvements we've been making to Neon's serverless driver. And by the way, if you prefer this kind of information in text form, there's also a blog post that lays it all out that way, the link at the bottom of this slide. So first, I'm just going to take two slides to make sure everyone's on the same page here. Neon offers serverless Postgres. That means quick, simple deployment, no servers to manage, and scalability all the way from nothing up to really high levels of demand, in addition to branching and the other benefits that Neon offers. Now, I think it's only natural to imagine that users would want to connect to their serverless Neon databases from serverless computing platforms. But there's a problem. Postgres connections are made over TCP, and modern serverless platforms like Vercel Edge Functions or Cloudflare Workers generally don't talk TCP. So until now, you had an unfortunate choice. You could have either serverless Postgres or serverless compute, but you couldn't make them talk to each other, so you couldn't have both at the same time. Neon's serverless driver solves this problem by redirecting the Postgres wire protocol over WebSockets. This makes ordinary, fully functional Postgres connections accessible from new environments, including serverless platforms like Vercel Edge Functions and Cloudflare Workers. The driver is built on top of Node Postgres, and it's a drop-in replacement for it. So where you previously have typed npm install pg, and potentially also brought in the TypeScript types, instead you just need to type npm install neon database /serverless. The serverless driver works with any Postgres database, but if it's not Neon, then you have to run your own WebSocket proxy, and there are instructions for how to do that in our driver GitHub repo. Okay, so that's the context here. Now, a key feature of the serverless environments where our driver is useful is that state generally isn't persisted from one request to the next. That means that we can't use ordinary client-side database pooling. Instead, we have to make a new connection on every request. And that makes the time taken to establish a new database connection particularly important. So we've been working and are continuing to work to speed up that connection time. So how do we achieve this? Well, unless your database client is right next to your database, the great majority of the time that it takes to make a connection will be spent waiting for data to travel back and forth across the network between client and server. And that, of course, means that there are two key ways that we can reduce connection latency. The first way is that we could just make those network round trips shorter. And we could do that by putting read replica databases across multiple regions, so there's always a database near a connecting client. Read replicas are coming. They're an important item on Neon's roadmap, but they're not available yet. So second, of course, you could work to make those network round trips fewer. And that's the main thing I'm going to focus on today, bringing down the network round trip count in order to reduce the time it takes to get back your first query result. Our first attempts to connect Postgres over WebSocket took no fewer than 9 round trips, and those 9 can be broken down as follows. 2 round trips were taken up by the 3-way TCP handshake and establishing a WebSocket connection. A third round trip was spent asking Postgres if it supported TLS, and Postgres responding to say, sure, it did. Round trips 4 and 5 then negotiated the TLS encryption on the connection using a C language TLS library that we compiled to WebAssembly. It then took a further 3 round trips to identify and authenticate the client with the database, bringing us to a cumulative total of 8. And then on the 9th round trip, the client would send a SQL query and the database would return the result. And subsequent queries were then 1 round trip each. Now, of course, just how long 9 round trips takes depends on the length of the round trips. But the worst case, when client and server are located in different continents, could be pretty long. From beginning to end, it could be more than a full second, and we'd really like to be able to save some of that time. So if we start with the left-hand side of the diagram, it turns out that we can bring these first 5 round trips down to 3. And the first change we make is to switch the way we encrypt the connection. In this original flow, we set up an unencrypted WebSocket and tunnel an encrypted Postgres session inside it. And the way the Postgres protocol currently works, you have to spend a round trip asking Postgres if encryption is supported before you then set up the encryption. So what if we switched the encryption round and took an unencrypted Postgres session and tunneled it inside an encrypted WebSocket? That actually saved us a round trip because this way we get on and establish an encrypted connection before we talk to Postgres, so we no longer have to ask Postgres about TLS support. And then actually it saves us another round trip too, because unlike the WebAssembly TLS library that we started out by using, all the modern platforms that we might be connecting our WebSocket from support TLS 1.3, and TLS 1.3 usually only takes a single round trip to establish a new connection. So that brings the original total, which was 9 round trips to the first query result, down to 7. And what about the right-hand side of the diagram here? Can we make similar improvements there? Well, let's have a look at what's going on in exchanges 4, 5, and 6, the ones that authenticate the client to the server. If we take these messages one at a time, the client starts by naming a user and the database they want to access, and the server says, fine, please choose one of the following authentication schemes. Now the client says, okay, I pick Scram SHA-256, which in fact is the only scheme that the server offered, and the server proceeds to send us an authentication challenge. Now the client has to compute a response to the challenge, which it sends back to the server, and then the server checks that response and, all being well, tells the client it's authenticated and can send over a query. And after that, of course, that's what the client does. Now, Scram SHA-256, or just Scram for short, which is what we see being used here, is a fairly modern authentication scheme. It's designed to increase the time and cost of a brute force password attack, much like bcrypt or scrypt or pbkdf2. Scram, in other words, deliberately burns CPU time by making us calculate repeated SHA-256 hashes. Neon uses the default work factor, which demands 4096 hashes. And at the time the Scram standard was developed, that was intended to take about 100 milliseconds of CPU time. Now, you may have already spotted that that's not really appropriate for connections from serverless environments. There are obviously latency implications, but it's also going to blow your CPU budget out of the water. On Cloudflare Workers, for example, the free plan is limited to 10 milliseconds of CPU time, and the cheapest paid plan is limited to 50 milliseconds. So an authentication scheme that was specifically designed to burn up 100 milliseconds of CPU time just is not going to work. Luckily, Neon needs Scram less than many other Postgres providers, and that's because all our passwords are randomly generated and they're therefore not vulnerable to dictionary attacks. If we want to make our passwords harder to brute force, rather than by slowing down password verification, we can simply increase the search space by making them longer. So for connections over WebSockets from our serverless driver, we drop Scram and we fall back to simple password authentication instead. That gives us a shorter, simpler authentication flow. The client sends the same startup message, but this time the server just asks for a password, we send the password, and the server authenticates us. And then, of course, we send a query and receive a result like before. So now we're down to a total of 6 round trips. But it turns out that there's another benefit to moving to password authentication. With a challenge response authentication scheme like Scram, some of the round trips are necessarily sequential. You can't send the response before you've received a challenge. But with password authentication, none of the round trips are constrained that way. None of the messages the client sends here are dependent on earlier responses from the server. And that means that we're in a position to tweak the driver so that we implement pipelining of these messages. In other words, we can fix things so as to send off these 3 messages all in one go without waiting for any response from the server in the meantime. And we can do that because we know in advance that the server is going to offer password authentication. In fact, if we run our driver in a web browser, we can see the change in the WebSocket traffic in the network tab of the developer tools. Without pipelining, these are the original 3 round trips back and forward to the server. And then with pipelining implemented, we send all 3 client messages in one go, and then get the same 3 server responses as before as the server catches up with us. Now, I was initially working on the driver in the UK and testing it against a database in Germany, and I could see that pipelining gave us a nice reduction in connection times. But I also did some testing where I put both the driver and the server in the same AWS region, and then I saw something a bit odd. In that case, the pipelined connection turned out slower than the ordinary unpipelined one. What was happening was an unexpected pause between the first and second replies we got back from the server, and that pause could last up to around 50 milliseconds. Some of my colleagues looked into that, and they discovered that the Rust WebSocket library we're using on the back end doesn't set TCP no delay by default, and we were therefore getting hit by TCP output buffering on the server. In particular, the culprit seems to have been Nagel's algorithm, which says that as long as there's a sent packet for which the sender has received no acknowledgement, the sender should keep buffering its output until it has a full packet worths of output. Happily, once we'd identified that, it was a one-line fix to set TCP no delay, and pipelining then made things even faster for all lengths of network round trips, even the really short ones. So by pipelining those three messages in this way, we've brought the total number of round trips to get our first query result down to 4. That's this single round trip to both authenticate and run our query, coming after the 3 round trips we discussed before, which set up a TLS encrypted WebSocket over TCP. And that's as low a number as we can reach for now. But there are a couple more important things we've done to speed up connecting to Neon with the serverless driver. First of all, in our earliest release, we were using a separate WebSocket proxy to unwrap the WebSocket traffic from the client and send it onto the server as TCP. And there was only one of those proxies, so it wasn't necessarily close to either the client or the server. And that meant that each round trip between the client and server was actually 2 round trips, and potentially quite long ones at that. So to fix that, we integrated a WebSocket proxy into our main Postgres proxy software so that every database is accessible just the same over WebSockets as over TCP, and there are no extra round trips involved. Secondly, it used to be that authenticating the client required the server to wait on a behind-the-scenes network round trip to our control plane, which could be in a different region. And that again added to the connection latency. And so we fixed that by adding some caching so that this behind-the-scenes round trip is rarely needed. Of course, we want to keep on improving performance and driving down latency. And one way we might approach that would be by making use of web transport or HTTP3 WebSockets when those arrive. Both of those options use QUIC as the underlying transport. And one of the benefits of QUIC is that it effectively combines the TCP and TLS connection steps, and that would save us at least another round trip. Finally, I've been talking today mostly about the time to a single first query result, but of course there are also cases where it would be useful to make several independent queries over the same connection. Postgres itself already has support for pipelining multiple queries, but the Node Postgres library that our driver is based on doesn't. So that's another area where we might be able to speed things up in future. Okay then, thanks for watching. If you haven't tried out Neon and our serverless driver yet, please do take a look. This link, neon.tech/driver, should get you started. And we're really looking forward to seeing what you build. Bye-bye.